All right, we're ready to start. So hello everyone, and welcome to the electrochemical colloquium. Today we're discussing oxide surfaces. As you know, oxides are very accessible materials, so many people work with them and they're relatively easy to make. And they're used in catalysts, as electrocatalysts, as batteries, fuel cell materials, and there are, of course, many other examples. But the fact that the synthesis of oxides is so accessible, of course, does not mean that we can be sure about the quality of the resulting materials, especially when it comes to the quality of surfaces, because oxide surfaces can be extraordinarily complicated systems. When we perform electrochemistry on such oxide surfaces, we should be very careful about how we interpret the electrochemical response. Ideally, for this, we need to understand the atomic structure and physical properties of such surfaces in real experiments. So our today's speaker is Professor Ulrike Diebold, who is an outstanding expert in physics and chemistry of oxide surfaces. Ulrike received her PhD in physics in 1990s and her habilitation in 1998, both from Vienna University of Technology, and she had been a professor of physics in Chilean University until 2009. In 2010, she moved back to Austria, and she became a professor of surface science in the Institute of Applied Physics at the Vienna University of Technology. Ulrike, we're really happy to host you here today. Thank you for coming, and now the stage is yours.
Okay, thank you so much, Andrew. I hope you can see things. Yeah, and so first I want to thank Andrew for organizing this. You're really doing the community a wonderful service. I am overwhelmed by the number of people who take the time and log in, and I can tell you from my own experience that I often don't find the time when the live colloquium is taking place, but I look at things later and I have learned a lot. So yeah, thank you very much. So my research area is oxide surfaces. And what I try to, I guess the main message is that we really try to understand the atomic structure and how it relates to single molecule surface chemistry. And I also very much believe that this is relevant for the electrochemical community. But we're coming from a different angle. So what we do is what's called surface science, where we try to get mechanistic insights into fundamental surface chemical processes at this single molecule atomic scale. So what I call it is, it's not what we do is, I mean, the methods we use can also be used for characterization of oxides and other materials. But what we really try to do is what I call experimental modeling. So we use very tightly controlled conditions, so sample and gas atmosphere and so forth, to really have a very good handle on both the sample and the environment, and then trigger some chemical processes. And the reason why we do that is that people have idealizing. So I come from a physics background, right? So in physics, we deal with a spherical cow, so to speak. So something we try to idealize things as much as possible, and then slowly go back maybe towards more realistic materials and conditions. And the thing, you pay a price because you're really not very realistic anymore if you do that. On the other hand, you really get the upshot is that you get very close interaction with theoretical modeling. So especially density functional theory or first principles molecular dynamics. So this is where we come from. And, yeah, I just early on in my academic career, for many reasons, I decided that metal oxides are interesting. They're abundant, they're very versatile and robust. They're very interesting as energy materials for many things, for many applications. Many of them really rest on electrochemical processes. So when I say controlled conditions, then what I mean is where we come from when we do classical surface science is that we conduct our experiments in one of these ultra high vacuum chambers, where underneath here there are some pumps. So we do this in a pressure of 10⁻11 millibar. So very far away from what real electrochemists do. So not only dry instead of wet, but also very low vacuum, low pressure rather than ambient pressure. And then typically also, so what we like to do, microscopy with atomic resolution in combination with all sorts of surface spectroscopies, because that gives us really this atomic scale insight. And we do that, the best images we get are really at 4 Kelvin. So it's not only the atmosphere, it's also the temperature, and then also we like to use single crystals. So, if whatever I say here is really very idealized, but really what we try to hope is to get some fundamental insights that then people can use in their thinking about, more realistic chemical processes. So just a typical example. So this is a material I've been working with a lot, rutile TO2 110. So this is a density functional theory model of the surface. You would have surface oxygen atoms, titanium atoms, surface oxygen atoms. Some of these oxygen atoms are removed because of the way we prepare the samples, single crystalline samples, and then you see oxygen vacancies. So this is a non-contact FM image. You see these rows of these oxygen atoms, and some are missing. You see these vacancies. And the way we do these experiments, we can look at the oxygen atoms, but we can also look at the electronic structure. So this, for example, would be excess electrons that are trapped in the near surface region. Doesn't at the titanium sites, doesn't matter where, but things like this we do quite a bit. And then what we can also do is this is an old STM movie, so this is many images that have been taken over the course of hours. Here's one single hydroxyl on the surface. So this is in empty states STM. The theme of my talk today is single hydroxyls, right? This would be an isolated OH group. And that has been actually gotten there. So this would be an OH group on a surface. We know from many experiments that that's what it is. And then we take this, I show you this movie, and in this movie, one single water molecule comes, probably hops around on this titanium rows, dissociates, and makes 2 hydroxyls. So if you look here, there's some oxygen vacancies, 2 OH groups are formed and then move apart. So, very simple chemical process, right? A dissociation of one water molecule, but with really intricate insights. So this is experiment, right? This is not calculations. This is really experimental experiments. So that's what we do. And so for today, I will have the talk in 2 sections. So the very first one, I want to give you, some of the latest results of the great things we can do with our surface science methods with single crystals, low temperature, and in very, very good vacuum. And what we really want to do here is we want to measure some very fundamental properties that are somewhat related, of course, I think, and I'll tell you then in a second why, to what people think about the interaction of oxide with aqueous solution. So what I want to show you is that we use the tip of an atomic force microscope. So this would be the very end of the tip of an atomic force microscope, modified in a certain way. These are OH groups, like the ones I showed you before. And the different OH groups, hydroxyls on the surface, have a different, we relate it to a different gas phase proton affinity. So these are measured values, okay? And I want to show you how we do it. So I'll go a little bit in technical details. I can imagine that maybe for some of you who are really electrochemists, maybe that's a little bit too technical. So if I will come back in the middle and we'll make a clear break, where I'll start with philosophical remarks, and then this second part, I go to try to connect then this ultra high vacuum world that we live in with the world that a little bit more with the world you guys live in, which is aqueous water. Okay. And then a common theme is what Andrew referred to in the very beginning, that we really think, all our thinking analyze that if you really want to get fundamental mechanical insights in elementary steps, you need to know the atomic scale structure of our surfaces, so that's really the common theme. Everything else, if you remember this, everything else, is just extra. Okay, so coming back to this first part. So, if you're really a chemist and, don't care about UHV surface science, of course, I think you should, then you can tune out now for the next, 25 minutes or 20 minutes or so. So let me start with something very simple, the Bronsted acidity of molecules. So in the gas, in water, what you have is, let's say, acetic acid, that's a weak acid, and then in water you have some probability that this dissociates. The proton is dissolved in the water, and then you can measure the acidity constant here, and then depending on the change in Gibbs free energy, this rate constant will be faster or slower, depending on the temperature, of course, and the logarithm will give you the pKa, which for acetic acid happens to be 4.7. Okay, so this is what happens in water. And in gas phase, you can do the same thing in principle. So you can also take away this proton and have two fragments of this molecule in the gas phase, negatively and positively charged. And this is so-called proton affinity. And you can look up in this NIST data table what this proton affinity is. It's tabulated for most common molecules, and it has to do, of course, with the acidity, right? Because of the molecule, because it's easy to give off the proton, then it's more acidic. If it's harder, then it's more basic. And these two are related in some sort of thermodynamic cycle. We have here, the change in the Gibbs free energy when this proton is separated or not, and then you have the same thing in aqueous solution, and then you have the solvation of these. If you can go around in this cycle if you take each of these fragments and then dissolve it, and then somehow determine this delta G of the solvation. So those are the two things that are connected. Now, since the first part of my talk is strictly in ultra vacuum, we really have no handle on this lower part, but we have a handle on this other part. And I think even this upper part, what happens, how easy it is to remove this proton, the proton affinity, I think is quite relevant for oxide surfaces. And the reason is why, so if you think, so for a molecule, of course, it's one proton that you can get off, or maybe two if you have more than that, but surfaces, any surface, especially oxides, are very heterogeneous, right? So you have first of all many different possible, places where atoms are. They have terraces and kinks, and they have adatoms and vacancies and dopants and all those things. So because surfaces are heterogeneous, and it says an oxide surface, then these hydroxyls, depending where they sit, can also, you think about, giving off this proton much more easily or not. Even if you have something that is not so, so terraced and so defective yet, if you just think of a perfect single crystal, like I showed you the STM image before, even there you have different oxygen atoms on the surface. So these were the bridging oxygens I showed you before in STM image, and here would be a water molecule, and then depending how easy it is for the water molecule to give off one or two protons, it depends very much which oxygen atoms you look at here, right? And so these are really nice work. There's lots of things going on with molecular dynamics simulation. So this is an older work by Michael Sprigg. And there's again this thermodynamic cycle where people try to really calculate this pKa of, let's say, TO2 in water. There's really no way to compare these calculations to any experiment. The only thing one has is the point of zero charge, right? So you can go, for example, to this nice compendium of point of zero charge point of zero charge. And can, the way it's measured is just by putting these materials in changing the acidity pH of this of the electrolyte or solution, and then when it's at the point of zero charge is when it's uncharged. So that's what you can get, but you have that's a really overall property. Sometimes people do it for different facets, but it can be very different for different atoms, right? So that's the question that we had. So we can look at these things. We can look at these surfaces with atomic resolution, and in fact, I should maybe point out, so I get a little bit more into the details. This is actually a non-contact AFM image where we measure the frequency shift when this tuning fork, so here's an STM tip, so a sharp needle, this is about 10 millimeters or so in size here. So we bring this in front of the surface and we measure the resonance frequency when we have this when the tip of this non-contact AFM interacts with our surface. So what's shown here is a change of the resonance frequency as is scan across the surface of this tuning fork. What we really look at here is the chemical interaction between this very last atom of the tip and the atoms on our surface when they're in very close distance. So very close, maybe half a nanometer or so separated from each other. So just generically, if you think of two atoms, you bring them closer together. This is the interaction potential, very generic in black. So this is the distance in picometers. At some point, you have the equilibrium distance. If you take the first derivative, you get the force, which is 0 here, and there's a minimum somewhere here. And then if you take the second derivative, this is something like the stiffness. And here, the change in resonance frequencies, that's what we measure. And then we can, measure the change in resonance frequency as the tip goes in and out, approaches the surface and comes back, and then integrate that and get the force. So this gives really wonderful images. There's a very famous one of a molecule on the surface. So this is a molecule on the surface. This is this non-contact AFM images. You only get that when you have the tip under real control, atomic control. So in this case, it's functionalized with one carbon monoxide molecule. So what we want to do is now we want to probe these hydroxyls on surfaces by having this tip functionalized. So like the tip is our probe, how strongly this proton is adsorbed on the surface, right? With atomic resolution. That's what we want to do. So how strongly is a proton bound, which then has to do with proton affinity and surface acidity and surface hydrogenation reactions. So what we do is we have this wonderful atomic resolution images of a well-prepared surface with hydroxyls. We bring the tip closer, so we park on top of the surface, we go in and out and measure these force distance curves. That's what we do, right? Or that's what we do on single atoms. And it's a little bit of, you can think of, so what we really do is we have this hydroxyl here and it kind of goes close enough that it forms a hydrogen bond with an OH group. And then the tip and the hydroxyl on the surface kind of compete for this proton, like in a tug of war. And I will show today some results by Margareta Wagner, who's assistant postdoc in our group. And she did on this particular oxide surface. So there's lots of interest why I will not go into any of the details. Just this is the atomic model of the surface. And maybe the only thing that's interesting is in this context is that on this surface, it's a very perfect single crystalline surface. We have 1, 2, 3, 4 types of oxygen atoms. And the red are the oxygen atoms and green and blue are the indium atoms. So each of these oxygen atoms is bound to 3 indiums. in a little bit different way. So the bond angle and the bond distance of these oxygen atoms with the cations is a little bit different. And because of that, the reactivity of these oxygen atoms is a little bit different, right? So, so we named them alpha, beta, gamma. These are theoretical calculations of the valence band density of states. And, you know, if you want the HOMO, the higher the HOMO, the more reactive. So you would expect the beta oxygen here to have a different proton affinity than, let's say, the alpha, beta, gamma, delta oxygen atom. Right, similar if you have different oxygen atom molecules, depending how they are bound to the backbone, it will be different how easy it is to give off this proton. All right, so we can image this surface. So we can make the surfaces really, really beautiful and nice. And then we put a little bit water, vapor, into our ultra high vacuum chamber. And then what happens is that the water dissociates. Like I showed you this movie before, a water molecule comes down, dissociates, the proton gives off to an oxygen atom. Here, these what looks like propellers. These are always two different OH group hydroxyls. One is the water hydroxyl. So water comes. There's a surface oxygen atom, let's say the one here. The water molecule dissociates, gives the proton on this surface hydroxyls. You have two protons and you can distinguish them really nicely in these beautiful images. And then the nice thing, I mean, this is a very delicate method, but what you can do is you can actually, maybe not you, but maybe not I, but Margareta can take these protons and move them from one place to another. And then, so here there's already 3 hydroxyls in this image, one with surface, the water hydroxyl, the proton on a beta surface oxygen, and then a gamma surface oxygen by moving things around. Okay, and then what you can do is one can do these force distance curves. So you park, you identify which kind of hydroxyls you have, you move the proton from one on the other, identify there, sit on one of it, and then go in and out and do force distance curves. And this is many curves or many months, even years. And the different colors stands for different hydroxyls that we have on our surface. So this is the short range force in piconewtons. Coming in, at some point there's a minimum, you come closer, it increases again. And do that going in and out. And we have this characteristic, you can see it's characteristic for each surface hydroxyl. And the nice thing is that we then calculated and just modeled this in theory. So what I showed you before, these movies here, these are actually DFT calculations. And then you can do the same thing in these calculations and get the same type of force distance curve. This is the same Y and X axis. So, you know, there's really very good agreement. So for example, here, you know, the minimum, I don't know which one I should look at. Maybe the minimum here is, I don't know, 345 piconewtons, and here's 348 piconewtons in theory experiments. So there's really quantitative agreement, which gives a lot of credibility to the calculations, actually. So we understand qualitatively these curves. So one is, so it's really two things we look at. We look at the minimum, the position of the minimum, the tip displacement. So where is this minimum when you go on the different hydroxyls, and also the depth, you know, how deep is this minimum? So these are the two characteristic values we look at, the delta Z and the minimum. So the delta Z is so 0 is arbitrary. We just take this one. And then, you know, it's just when you come in with the tip, it makes some sort of hydrogen bond between the last oxygen atom on the tip and the proton on the surface. So it's like a little temporary water molecule is formed. So we can change this bond length here. And this geometric height of the hydroxyl. That's, you know, that's what we measure here for the different displacements. But more interesting is this this change of the minimum. So the minimum is how strongly does this oxygen atom of the tip interact with the proton on our surface. And really what we have here is if you take this bond length at the minimum, and you look at the bond length of this hydrogen bond, then there's a nice linear relationship with the force. So it turns out that when you have something that holds, it's like a tug of war, if the surface holds this proton very, very well, then, you know, you will not make a strong hydrogen bond. Then this is a shallow minimum. If it likes to give it off very easily, then there will be a more deep minimum. So this hydrogen bond between tip and sample is correlated with this minimum. Okay, so this is characteristic for each hydroxyl. But how do we get any sort of number? And this is now where we've been really brave. So we have here Bernd Meyer. He's a theoretical collaborator from FU Erlangen. What he did was, so he did these calculations. And he did these calculations for 3 molecules. So this would be, for example, this acetic acid I've alluded to before, with this proton affinity according to the NIST database, and he does these force distance curves for one free molecule and calculates a characteristic minimum for this type of tip. And he does this for, you know, a large variety of molecules, gas phase molecules, all tabulated. And this is the force minimum calculated. And you can see this is a nice straight line that we call our calibration line. So now we do something that's quite brave. What we go and we say, okay, we have the force minimum on our surface hydroxyls. This here would be here at 250 piconewtons. So 250 piconewtons, then according to this would be this proton affinity. Okay. Then we can do that for the blue curves. And then we would have a proton affinity that's a little bit closer to this acetic acid. So, you know, a little bit more acidic than this one. And then we can do that for all of the others, right? So is this reasonable at all? So it turns out that the change, it's difficult to model absolute proton affinities, but changes one can model, and the changes agree really well. And also the PA values that we are getting are really in the right order of magnitude of what one need to expect. So we've really found a way to, we think, determine or relate to these surface hydroxyls, 4 of them, 5 of them, the proton affinities. So that's very nice. The question is it how transferable is it? So we then tried to do this on another material. This is the TO2 surface I showed before. This is a hydroxyl here. So by the way we do it, we prepare the tip on this indium oxide surface. We have good measure. Then we take it, we go to another material, measure force distance curves there, and then go back to the original one to see it's close, and do also the modeling. And then we find the surface hydroxyl on this CO2 is, as expected, much more acidic. So that's what the first part I wanted to show is we have found a novel method to evaluate surface hydroxyls one by one. And in principle, we can do that at regular, show that these heterogeneous surfaces, right, before. So our dream is to do that at regular surface sites, at steps next to defects, dopants, other sort of molecules, and so forth, and really figure out how the proton affinity of oxygen atoms and different oxides are, and then hopefully give some kind of benchmark also to this theoretical calculations. So this is the first part of what we're doing. So so this is where surface science stands at this point. So I want to take a little break here and just give you people a chance to ask some questions if there are any.
Thank you, Ulrike. So the audience can ask questions. Please feel free to unmute yourself and ask questions if you have any. And maybe then I can start. I'm curious, when you showed on the slide, I think 22, the proton.
Mm-hmm. Yeah.
So when you're probing that H bond length, in calculations, you probably did not consider the fact that a proton has its own ability to tunnel. So there is some nuclear effects in that sense. So do you think it really matters in your experience? Because in your experience, you can really measure it directly. And we have a lot of these questions about the role of proton tunneling in catalysis and chemical reactions.
Yeah. So I should say that we control the tip, we control the distance so that we don't really take this proton off the tip, right? So we just look at this, essentially this formation of the hydrogen bond between the tip and the sample. We don't, if you go any closer, so we can go any closer, then often we pluck this proton off the surface and then our tip changes. So we stay in this regime. In that sense, we don't really go close enough that we have this tunneling effect.
Mm-hmm.
What we haven't done in principle, I think we could do, but we haven't done, is you could, of course, repeat these experiments with D2O and see if there's any difference. I think it would be an interesting question, but we haven't done that. Yeah. So we really don't take the proton really off. We just say, okay, how is it related to this hydrogen bonds between the tip and the sample? That's really what we're probing. Okay.
Right, but you're pushing that bond sort of in. So
yes, we go close enough. We go close enough. We go close enough. So we don't really go beyond. Beyond the. Okay. That's how I showed this curve. Okay. So what we do is we measure the green line and then we integrate once and measure the red line and show you the red line, but we're really not going to where we would really be closer than the equilibrium distance. So because if we do that, then it is a really danger that we really take off this proton from the surface.
Right. Okay. One good question that comes from the chat is, I think it's good because it's so basic, but then probably you can interpret it the way you we're just curious how you think about this. How can we have all different oxygens on a single surface? So why different oxygen sites are different?
Okay. Yeah. So
say if just a second, if for a metal, it might be also different, but maybe not to such an extent. Right.
So we have here, okay, if you look at this one here, right, where people have done these calculations, and I've shown you the same on tier 2 STM, right? So this is maybe easier. That's very clear. So this is the surface, and then here would be the bulked volume, right, that we've just cut off. These oxygen atoms in the bulk, they have 3 neighbors, and they have also 3 neighbors here of the surface, but these oxygen atoms have only 2 neighbors because one is missing, right? So these oxygen atoms are clearly quite different from those. And then in the particular case of the indium oxide that we use as our test bed, it just so turns out that this indium oxide it has a big spheroid structure. That's a very big unit cell. And then just from the bulk structure, the bond lengths of each of these oxygen atoms even if it's perfectly crystalline, the bond length and bond angle is just from the bulk crystal structure a little bit different, right? If you have a different bond angle and bond length, then maybe here. Then the density of the local density of states, or the local orbitals, if you want, of these oxygen atoms is a little bit different. So that's when it's perfectly crystalline. And then if you have an oxygen atom at the step or at the kink or something like that, then you would also expect that it would be different because it just is a different chemical environment.
Right.
Does that answer the question? Yeah.
Oh, yes. Yeah. No, I think for me, it's
Yeah,
pretty
okay.
clear. Yeah. This looks.
But it's good to have these questions. Yes, absolutely.
I'm also curious what you can comment on the accuracy of, so how accurately for a DFT calculations, how accurately can you reproduce the properties of the surface that you measure in real STM experiments? So the density of states, or maybe the adsorption properties, and something else that you measure in surface science. So if you're really careful, you know where locations of the atoms are, can you just use then the DFT to really get the right numbers? Or DFT is still pretty far from what your experiments, even for a perfect surface, would show?
So I must admit that for perfect surfaces where we know the structure, it turns out that DFT is often really predictive already, right? So I must admit they have almost surpassed us, right? For if we know the surface structure, so for example, in this, for this surface, indium oxide, okay, that we have a collaboration with Bernd Meyer, we're just about to submit a paper where we have looked at not just single hydroxyls, but like more water molecules on these surfaces. So it's still ultra vacuum and low temperature, but like if you want the first inklings of ice formation on the surface. And it turns out that we had published with Bernd a paper 3 years ago when the supplement he predicted water structures for higher coverage than we were able to measure at that time. And in meanwhile, we have measured them, and the absorption energy is really quantitatively predicted by what he does, right? So, I mean, there are still then things that, we see that theory hasn't thought about, right? So there is still, right now, we're really like in lockstep. So if you have a very good theorist who knows how to, do these DFT codes and what kind of, approximations to really take, it can be really to an extent where we can actually predict things like absorption energies, structures, and so forth for relatively simple systems. I think it's accurate enough.
Okay.
Some of the things.
Okay, interesting, because there's so many things. I mean, the DFT itself it's so much dependent on the functional and so many other things.
Yes.
That I was just wondering.
Well, that's why, for example, for the CO2 surfaces, right? We collaborate quite a bit with DFT people, and the question is how localized the electrons. And our experiments have been helpful to find out what kind of DFT plus U Hubble tube to take to really find the right localization for titanium dioxide to really model things accurately. Okay, so I think at some point, it's almost like sometimes what we do is an experiment is a benchmark for the DFT calculations because we have this nice atomic control.
Okay, that's exactly what I was saying. So it's coming really, the two approaches converge.
Yes, absolutely.
That's interesting. Okay, we have so many questions in the chat, so I would really recommend asking directly because many of them probably need more details. And maybe in the meantime, I'm wondering, maybe you can just tell me from your perspective, from your experience, when you have adsorption of molecules on any surface, especially on oxide surface, it's very important for oxides, what really determines the adsorption strength? So we can say, okay, the site itself, the electronic structure, but what in electronic structure is the most important?
So for it's different for which kind of molecules, right? So for water to stay there, it is, so water does two things. So in one case, so you have the oxygen of the water molecule, and then you can have hydrogen bonding. And so what you want to have is, so you have this lone pair on the oxygen that donates charge to that interacts with the cation.
Mm-hmm.
Right, and then here it depends on the electronic. So here it depends essentially how, if you like, the Lewis acidity of the cation, if it goes there, and how strong it binds. But almost equally important is the interaction between the hydrogen bonding. So you can have the water molecule will bend over. So like here, okay, take this one. Where is it here, for example? Okay, so a water molecule will bind to this cation, and then at the same time it will make a hydrogen bond to one of the surface oxygen atoms. And then it depends on the distance between. It depends very delicately. People have published so many papers, and I've written actually perspective. If on this surface, if the water molecule dissociates or not. So is it better to put down the proton on the surface oxygen atom, or is it better to have it there? And that depends on the strength of how strong is it bound here, and what is the distance, how far away is this oxygen atom. But this can really stabilize things. And then we have more than one water molecule, then this hydrogen you can also have hydrogen bonding to the next water molecule. Mm-hmm. So there's this whole network that we can actually image with this non-contact AFM very nicely.
Okay, and what about the bulk properties? Do you think that the electronic bulk properties are, I mean, they are important, but to what extent? Because here's the surface, the near surface layer has its own electronic structure often, may have surface states and so many other things.
Yeah, but in the oxides, actually, there's very little in terms of surface states. So you just take the bulk bulk electronic structure, and then on the surface, it may be shifted a little bit. But generally, there's most of these, it's not like you have a separate surface state like you have on a metal.
Okay. We have a question from Imeng.
Hi, hello. Hello.
Hi.
Ulrike, hello. Very nice talk. I have a question regarding this very interesting TiO2 surfaces. I'm from Donghua University in China, so I'm a spectroscopist, mainly on transient absorption spectroscopy for water splitting. So my question regarding your TiO2 and water dissociation is about when we do water oxidation, we have, for TiO2, we have multiple reaction sites, and then these charges coming together to oxidize water, at least the two waters. So in electrochemical language, we often think the reaction, the active reaction sites might have to interact with each other. So in your experiment, do you have to consider the hydroxyl is an isolated reaction site, and then you look at this hydroxyl interaction? Or do you have to consider these two reaction sites interacting with each other, and then do this very interesting AFM experiment?
Yeah,
so how applicable of your theory to this multi-site reaction? So this is my question. Thank you.
Yeah, very important and interesting question, I think. So in this particular case, what we've done is we've really looked at isolated hydroxyls in the sense that they're far enough from each other so they don't interact with each other. But it's a very good question that when you have something nearby, how does that change then the surface acidity, right? So I can in principle think of having something close by, and then this other adsorbate, this other reaction product will change it. We haven't done it yet. I mean, this is really a very novel type of thinking about it or measuring things. But in principle, I think it's a very good question. So we have even more, right? In these experiments, we have an even more idealized system in the sense that they don't interact with each other. But you're absolutely right. It can really change things quite a bit.
Because hydroxyl is so important, especially when we do water splitting in alkaline environment. And, this is the thing that we concern. When we come to understand our surface, we get help. We might have to get help from the theoretical calculation, and then this interaction. I think it is called Franken isotherm theory, or if it's long mu, that means the single side is itself, and then we do all this reaction things. But when we come to Franken, we have to think about this lateral interaction. I think that might be very important for the electrochemistry process, how we understand the reaction.
Yeah, I agree. What can I say? I agree.
But I have to say your FM technique is so fantastic. I'm so into understanding what you have been doing. So it's really good work.
Okay, thank you.
Thank you very much. Wonderful answer. Thank you.
Thanks, Ulrike. I think we can continue.
Okay.
And then we'll have another Q&A session afterwards.
So actually, maybe it goes a little bit closer towards. So let me make some philosophical remarks about these atomic scale insights, right? So I can imagine that electrochemistry people is like, why is she telling me all of this, right? Ultra high vacuum, single crystals. Okay, single crystals maybe, but get a better handle on the material, but low temperature. I mean, we do this ultra high vacuum to really keep our samples clean, right? So you should take into account, first of all, that when this is ultra high vacuum 10⁻11 millibar. If we have a pressure of 10⁻6 millibar in our ultra high vacuum chambers, which is really pretty low pressure, and everything that's in there sticks on a sample because, let's say, it's cold, then that means our sample will be covered in one monolayer in 1 second. Okay, so that's 10⁻6 is not much, right? It's 10⁻9 atmosphere 1 ppb. So that's where we do it. But how does it relate to anything? But in DFT calculations, if you think about it, to solve the Schrödinger equation, right, where this is the kinetic energy of the electrons. This is this correlation between exchange between different electron-electron interaction, the hard part, that's all put in this functional. And then here you have this interaction between the atomic cores and the electrons, right? It's this so-called easy part. So for example, when you do surface calculations, you set up a cell as big as you want. So your computer allows you to, within reasonable computing time, and you put some vacuum in between, and then you minimize this. You change the energy until you have a minimum, and then this is the surface structure. So this is really in DFT. What you have is you have a perfect single crystal. You have a perfect vacuum, and you have 0 Kelvin, right? So it really, I think that goes back to Andrew's question. I think it really relates really, really well in terms of setup. Computational and experimental setup are really almost the same, right? And then in DFT, what you can do is, what one can, for example, think of water and look at it explicitly, like in these molecular dynamics simulations, but very often people just put the dielectric constant, like in VASP soil, right? Or you can put the gas atmosphere, the temperature with the chemical potential. But really, that's the essence. It's just, like an offset, a straight line, essentially. What calculate is the surface energy of this particular setup, and then you take into account, the dielectric constant or the chemical potential. But really, that's the essence, right? So it's really what people calculate is what we measure. And then, this is a very famous paper, right? Thousands of citations. Very nice, really, very famous by Jan Rosmeisel and Jens Nørskov, where they looked at exactly this rutile 110 surfaces, like the CO2 surface I showed you before, right? And then they looked at this electrolysis of water on these different oxide surfaces, so ruthenium oxide, iridium oxide, CO2, they all have the same rutile structure, always the 110 surface that I showed you, the nice STM images before. And then, what you do is you do this thing that, you take this, you take the water molecule and you take the electron and the proton and you look at the change in G, and then you do it at a difference. And so really what these calculations are DFT calculations, right? Perfect vacuum, perfect single crystals, 0 Kelvin. And for UHV surface science can agree really well, as I showed you. And as I, not always, but for simple systems, it's really well. But, there's a real question, right? Is this part correct? Because if this part is not correct, if you don't know where the atoms sit, then it's not clear if what you calculate is really relevant. So, are these surfaces the same once you stick them in liquid water? And the second question I have really asked myself, and maybe someone in the audience can answer that for me. I've looked through the literature, and I don't know if all these intermediates are really the intermediates people have looked at, right? And I cannot answer the question. That's actually, I have a question on the audience. Everyone uses the same, essentially everyone uses the same kind of setup, and take into account the electrochemical potential here in this relatively simple way. But are these intermediates the same? So I have no answer to that, I must say. Maybe you guys have, or one of you, what people in the audience has. But what we try to find out is if the surface structure stays the same, right? So that's what we do. And I should mention that for simple oxides, you know where to start. For other things, so when Andrew invited me, he alluded to perovskites and spinels, and we've looked in ultra vacuum, for example, maybe perovskites, and what we found out is the perovskite structures are a zoo of surface structures, right? You take this, and people always say, okay, you have the AO termination, the BO2 termination, and look at those, the period. And in reality, it's like, depending on the surface chemical potential, you can have all sorts of different surface structures, right? Some of them will dissolve, AO terminate surface dissolve in liquid water. So it's just a thing of caution. And I must say, sometimes it upsets me a little bit because people believe DFT calculations of very complex systems, but they don't believe UHV surface science experiments, at least it's experiments, right? So anyway, that's my philosophical kind of intermezzo. So the next part is then how does the atomic scale surface structure change in response to liquid water? But Andrew wants to say something. Yes.
I'm really sorry. Just wanted to ask you before on your previous slide. This is where you can just make a further comment. How often do you see surfaces to be ideal? Like ideal surfaces, bulk terminated surfaces, the ones that people often calculate in DFT methods?
In ultra vacuum, for the lowest energy surfaces, I don't know how often. It's a difficult question to answer, right? So we look at what's called the surface reconstruction. So that's the geometry of the surface change. We know, for example, for this TO2 110 surface, it doesn't, it's fine. It turns out for the iridium oxide surface, for example, the 110 is in fact not. We've published a paper together with Carsten Reuter last year. For the iridium oxide, it turns out the 110 is not this lowest surface energy. The 011 is, which is a different surface, and actually that reconstructs, right? So there's a lot of things to be known. I mean, I cannot answer this. I can answer for the ones we've looked at. I can tell you if they're stable or not, and then you can look at different chemical, oxygen, pressures and temperatures. But for very simple surfaces, there's a good chance that they are. For something that looks simple, like perovskite oxides, I can definitely tell you they will not be AO or TO2 terminated. I can tell you it will not be the case.
This was the question that was about. Yes. So for the
perovskite, for sure, it has nothing to do with reality. That I can tell you.
Okay, thank you.
Okay. All right, good. So we ask a very simple question. How does the atomic scale structure of oxides change in response to liquid water? And we're just talking about like open circuit potential. So just liquid water, no electrochemical applied potential, okay? And so this is an example of what Andrew just asked. This is the rutile TO2 011, not 110, but 011. So it's a diagonal, so it depends how you cut it. 011 is different, and it's reconstructed in vacuum. We know that, and actually this is work from Annabella Zeloni, and we've published papers together that in ultra-high vacuum it reconstructs. And she starts with this surface that you've identified of reconstruction. So the top surface atoms look a little bit differently. And then together with Uli Ascher, these are first principle molecular dynamic simulations for a relatively long time step. This is liquid water. And the liquid water, if you look, changes the surface. So its surface structure after a while really will change. Okay, so it will go back, you know, and really change towards what we call a 1-by-1, a bulk terminated surface. You can see there is some bond that formed here. So, so this is, you know, this is the 2-by-1 surface reconstruction, so the reconstructed one, and the 1-by-1, the unreconstructed bulk terminated one. This is time step and total energy in this first premise work. And it seems like the 1-by-1 is more stable, even though in the beginning is not, right? So, okay, which kind of questions my own research area a little bit, right? Even if we know what the surface reconstruction is, answering Andrew's question in ultra vacuum, does it stay? Is it the same once you stick the sample, the single crystalline sample, in liquid water? So that's really a question that we have been asking ourselves. So Jan Balaika in my group, he did his PhD, this isn't that. I said, okay, Jan, please, you know, stick TO2 100 and 011 samples in liquid water, prepare a nice surface, look if it's nice, expose it to a drop of liquid water, and then look again and see if it stayed, you know, the surface structure the same. And it turns out that this is not so trivial, because he tried first many different times. He tried, you know, of course the water we use is as clean as possible, you know, it's molecule water and outgas and everything. He tried to do that in some sort of glove box and, you know, under a stream of ultra pure argon and things like that. He got different results each time. And then, but you know, the problem we have, right, I told before, the reason why we do things in ultra vacuum is because we want samples clean, right? So a little bit of surface contamination really screws us up. We cannot get atomically resolved images anymore. So it turns out that all the things he did was really too dirty, right? So he didn't, because, you know, what we want to be, the reason why we want to be in ultra vacuum is we want to be way below this 10⁻⁶ millibar. This is where we like to live, and this is where liquid water is. So it's just, you know, it's a triple point. The basic thermodynamics, nothing you can do about it. The only thing you can try to do is you can try to be as clean as possible. So what then Jan and other people in my group came up with was that we dose water in we made a little special setup where we have here, this is an ultra high vacuum chamber. This is our scanning tunnel microscope. This is our X-ray photoelectron spectrometer. There's a little side chamber, ultra high vacuum chamber, that's connected to the main chamber. In here, if you look through this window, you see a little bit tip. This is the tip of a cryostat. Everything is in ultra high vacuum. We can move the sample in and out without ever exposing it to air. And then if we do that, we can put the sample in. So what we can do is, if you look back here, this, if you have water ice at if you have water ice at low temperature, then the vapor pressure of water is very low, right? So here what we do is we pump this out. Here we have a little cryostat. So this is the end tip of a little cryostat. This is at liquid nitrogen temperature. And then we can open one of these valves with a water reservoir, put in water vapor, right? In ultra vacuum, we have vapor available. We put the water vapor and we form ice on this cryostat. And this ice this little icicle, is at low temperature. So the vapor pressure is low. So once the icicle has formed, you can open up, you can put in the sample, close again, and let this ice thing warm up, and then make a water drop and put the water drop on our sample, then pump out with a cryo pump, and then pump it out until the water is gone, open up again, take the sample and stick it in the scanning tunneling microscope. And if you do it in this way, then we can get surfaces where we can get real atomic resolution. So this is a CO2 surface I showed you in the beginning. These are the titanium rows. Here, single hydroxyls. There's a little bit of dirt, but very little. It's essentially identical to a surface that has been exposed to a little bit of water vapor in ultra-high vacuum. So, it's really, really very clean. And I can tell you this is exactly the structure that we had before. So nothing has changed on this CO2 110, which is the lowest energy surface. And if you look in with X-ray photoelectron with grazing exit, this is the oxygen 1s, this is the clean surface, and this is after we have exposed it to liquid water in this little side chamber. And you can see a little bit of a shoulder. This is because we have a little trace of OH groups forming on the surface, but really very little. And there's a little bit of hydrocarbons, but very, very, very little. And if you do the same thing, not like this, but it just exposed in air, even in residual atmosphere, then you get something like this. This is a 2x1 structure that actually has been reported by 4 other groups that do surface science, one in Japan, one in US, one in England, and one in Rome. They all got the same structure. We know when you do it outside of vacuum, what you get, this 2x1 overlayer essentially is because you have some, so this is XPS. We know that then you get quite a bit, up to 1 monolayer of some acetic acid on the surface. So we think that what you have here is actually dirt that comes from the air. And then, we went in this paper, went to quite a bit of, kind of speculate where it comes from. I will not go into the details, but suffice it to say, if you do things not in the ultra-vacuum chamber, then things are invariably dirty. Okay, that's what I can tell you. So, but when you do it under well-controlled atmospheres, then actually you can make STM images before and after. So this is this 011 surface where this first principle molecular dynamics calculations I showed you a little bit earlier predicted the surface would change back to bulk terminated 1 by 1, and in fact it did. Right. So that's what we do right now. So we do different things in my group. One is we really try to make hydroxyls and measure them with our non-contact FM, but we also want to see how realistic are these surface structures. And I want to show you one that is the other materials that Andrew mentioned when he invited me originally to the seminar. This is an inverse spinel structure. So spinels are used quite a bit in oxide electrocatalysis, I understand. So this is, this is magnetite Fe3O4001, which in ultra-high vacuum or a wide range of oxygen chemical potentials, meaning for many different oxygen pressures and temperatures, it has not the bulk truncation, the 1 by 1, but it has this surface reconstruction that, I could tell you all about. I've worked on this for many years. Anyway, doesn't matter. You take a single crystal, you stick it in the ultra-high vacuum chamber, you do electron diffraction. If you have a 1 by 1 terminated surface, you see only these spots in the electron diffraction pattern. If it's reconstructed, you see these additional spots. The unit cell is big in Will space and small in reciprocal space. So for that, we can immediately tell. And it turns out that when we put our water drop on this surface, it's clean enough, we can really do experiments before and after. And if we only do it for a little short amount of time, then the surface is still reconstructed. We still see these extra spots. But if we do it for a longer time, then we see that the surface goes back to the 1:1, meaning the surface really changes. So this is hydroxylation that is on the surface. But you can see it's a really nicely ordered surface, right? It's different from before. So an oxyhydroxide, it's self-limiting. If it changes, it doesn't change anymore. We haven't really solved this structure, but in principle, we would have the capabilities to do that. So we can, I think we can in surface science maybe go one step closer and tell you, okay, under these conditions, essentially open circuit potential and ultra pure water, this is the surface structure you should be looking at, right? So interesting side, we played around a little bit. It turns out that this, when we have the surface, we can put first atomic hydrogen on the surface. We can do really strange things. We can first put atomic hydrogen on the surface and then expose to, this is essentially also liquid water film 20 millibar. Then the surface will not change. It will stay exactly the same. So a hydrated surface will survive in liquid water. So yeah, so that's where we are. So maybe one more thing we try, people talk, can you put an electrolyte? Not yet, we're working on this. One thing we can do a little bit, we can change a little bit the pH of this water drop, this very clean water drop. So this is the Pourbet diagram of iron with pH. So I don't measure the pH, but it's pure water. So I assume I have I have this electrochemical potential and pH 7, so somewhere here. But we can change the pH a little bit towards more acidic, and we do that by putting. When we have this water drop, we open the valve and put in some CO2, and then if we saturate that at different pressures, we can go to relatively low pH values, and then can look what the surface did. So even we can etch under acidic conditions, and then what we found is, of course, that the surface is covered with carbonate. Okay, so that's what we are at this point. We haven't done it that much yet. This is part of the grant that started like last year. Several people that I also saw in the audience are working on this. We try to find by dosing high pressure liquid water. So first of all, if you dose this high pressure liquid water, contamination is not your but our enemy. As surface scientists, we found a way to do that with clean UHV. So far, what we have looked at is unreconstructed surface that survive, and then this reconstructed surface go back to 1:1. So that's how far we at. Yeah, I should, before I stop, of course, mention the people who did the work. So the last part was done by Jan Palaika, and Jerzy Pawelitz is our experimental genius in the group who designed this water drop. Florian Kraushofer did the measurements. The first, and under the guidance of Gareth Parkinson, who is our iron oxide person. And before that, I showed you measurements by Margareta Wagner, together with Martin Setwin, who is now professor at Charles University, and then Bernd Meyer did the DFT calculations, and very important is my colleague and friend and classmate, Michael Schmidt. Okay, that's it, summary. So proton affinity of isolated hydroxyls, surface science, ever better methods, ever closer insights. DFT is UHV. Surface structures are often surmised and probably unrealistic. And we try to bridge UHV and liquid water. That's a summary in a nutshell. So now if any questions, I'm very happy to answer them. Thank you.
Hi, can I ask a question?
Go ahead.
Sorry, can I ask a question?
Yes.
Yeah, okay. So I'm Manasi, I'm from University of Sheffield, a PhD student. I was wondering about the first half of your presentation where you showed about one water molecule on the oxide and it is experimentally done. So I was wondering, as I'm doing DFT calculation, I was wondering how to deal with one water molecule experimentally, and what are the challenges associated with actually having that single water molecule? Do you have any insight on that? Or
so I didn't quite understand the experimental challenges of having one water molecule and an oxide surface.
yeah, that's what I mean.
Yeah,
So how,
please.
Yeah, how exactly you can deal with single water molecule? Because later part of the presentation you showed water droplets, so it was quite like different than a single water molecule experiment. So I was wondering how difficult it is to actually, or how challenging it is to deal with a single water molecule experiment as opposed to a droplet of water.
Yeah, so for us, a single water molecule is much easier. We have,
okay.
if you have the experimental capabilities, meaning these ultra high vacuum chambers. I showed you a little bit these non-contact AFM measurements. So we use this is a really wonderful technique to identify what one water molecule does, or what this other person asked before, when you have two of them together or several of them together with a hydrogen bonding network. With this non-contact AFM, we can really image where it sits and also a little bit how it's oriented. The nice thing with this non-contact AFM in this way we operate it is that there is we can take atomically resolved images, and we do that under conditions where there is no field. But normally people do scanning tunnel microscopy, right? We have always a voltage, so that means a potential between the tip and the sample. That means a very strong field, and also the current, tunneling current. Non-contact FM, we can actually do that without current, because we know that electrons will excite the water molecule and maybe dissociate it, and also under no field. So for that, we can get really good insights on one water molecule on one surface. So if you want to have a benchmark for DFT calculations, we can tell you, yes, that's how it will sit. So there's no question we can do that. Doing this other thing, trying to go to liquid water, is more challenging for us because dirt is our enemy. Okay.
Yeah. And also, any particular reason for choosing rutile and 110 or 011 surface?
So we have done, so TO2 is quite interesting, lots of interest in that. We have looked at rutile for a number of years. It's nice because the single crystal is available. We've also looked at anatase, which is the more interesting, more interesting for catalysis, more interesting phase. So yeah, no, I mean, we try, it takes us a long time to learn how to really control a surface really well. It's not a trivial thing. Usually it's the life of one PhD student. But this is, TO2 is very interesting for many applications. It's even more interesting. We've looked at zinc oxide, tin oxide, iron oxide, sorts of things. So
yeah,
it's a good reason currently will go. Which one are you interested in?
I'm currently looking at anatase because I'm looking at applications in catalysis. So that's why I was kind of wondering if you have done any calculations, any experimentations on single water molecule on anatase specifically. So I'm looking at effect of DFT parameters or the method on the energies or the properties of a single water molecule on anatase. So that's why I was very keen on the
on the 101 surface. On the 101.
101.
Yeah. So actually, we did some. If you look back in the literature, we did something with Annabelle Celoni a while ago.
Celoni, yes.
Right. Where we really think that a single water molecule on the anatase 101 surface is absorbed molecularly. And the absorption, I think we also did some, at some point later some TPT. I'm not sure we published it. I think so, TPT, we get it's this. I know, yeah, we did some. I know it's some desorption energies that you can then correlate with
Yeah.
calculated ones. So
I'm also doing along with the water. I'm also absorbing acids, carboxylic acids, for
Right.
benchmarking.
Right.
So yeah, that's why I was quite keen in this topic.
Yeah.
Thank you.
Sure.
Yeah. Okay. Thank you.
Thank you.
We're open to more questions.
All right. Thanks, Professor, for the very nice presentation. I have a question about the first part of your talk, where you indicate that there's a difference in the hydrogen binding affinity between like beta and gamma hydroxyl groups. My question is, are you expecting the difference to be larger or smaller than the gas phase when you have liquid water on the surface?
I'm not sure.
Yeah, so yeah, this one's perfect. So imagine the gamma and beta, they have different proton affinity.
Yeah, right.
No, but this is in gas phase, right?
So, okay. These are calculations where the that Bernd Meyer did. So he put the proton, these arrows that change his differences in proton affinity, you can calculate, and you can also, this is measurements, right?
Right.
So the calculations, the differences in proton affinity, you can calculate quite accurately. You just take your DFT slab, you have your proton on whatever that was, the beta oxygen, and then you put the proton on the gamma oxygen, and you look at the differences in this, the differences in essentially the energetics between the two DFT slabs, right? So that's what's calculated here. And then you compare that difference, moving from one to the other in DFT calculations, then you compare that with what you would get, is it, so we measured the two values. Through the line, we go to these x-axis, and this x-axis can be calculated independently. So these are independently calculated and independently measured. So from the measurement, this calibration, we go down, and that fits quite well. What you cannot do is absolute values in DFT, but the relative ones, you can just calculate by moving one from one to the other. Does it make sense?
Right, yeah, but those are in vapor, right? Gas vapor, is that right?
Yeah, everything, this is DFT, right, remember? And this is surface.
Yeah, my question is
everything is at, 0 Kelvin, perfect vacuum, yes.
Okay, my question is, imagine that we have water on the surface. Yeah. Would you imagine that the blue curve gets closer to the red curve? Or you think they are going to be larger?
That's difficult to say, right? Because this proton could, of course, I guess it goes back to this part that we haven't really touched at all.
Right, the Salvation energy.
Salvation energy, yes.
Yeah. I'm just thinking if the Salvation energy is gonna say smooth out the difference, or it's gonna increase the difference.
That's a good question. Just from intuitive which way it would go.
Right.
I mean, essentially what we do, let me go in my thinking. Essentially what we do is, I have it here, right? Essentially what we do is we come with, when we do this coming in and out, we form a hydrogen bonding between an oxygen group here and here. So yeah, I'm not sure I would have to think more if it smooths it out. I mean, the thing is that the local density of states is really a very strong function of what you have on these things, right? So when you have, I have to think about it. I really don't know. I would think it's very relevant for these things, but because, so the question is if this solvation in a, if the solvations are different for the different entities.
Right.
If we assume it's not, then of course it should go in one by one. I would think it's also, yeah, no, I don't know.
All right. Right, that's
Okay,
fine. Thank you.
sorry for
No problem. No problem at all. This is very insightful talk.
I mean, the one thing I can tell you is this, of course, these pKa's. I have it here in my supplement, so to speak. These are the proton affinities of the different molecules, gas phase molecules, and these are the acidity, right? And there's a lot of scatter. So the force minimum, and if you want to make a calibration line here, the force minimum and the acidity is also a lot of scattered, but that comes from the pKa. You know, there's quite some differences in the way you dissolve them.
All right, cool. All right, thanks so much.
Sure, okay. Actually, yeah. Actually, I think that's even worse. You know why? Because we recently did an experiment where we put more water on the surface. Thinking about it from that perspective. We put more water on the surface and we found that in this region, water molecules, it's really hydrophobic actually. It's interesting. This part is hydrophilic, this part is hydrophobic of this unit cell. Very interesting observations. So maybe it's even worse. Okay, sorry. Next question, if there are any.
Hi, may I ask a second question? Sorry.
Absolutely.
Okay. Regarding the second part, am I right in thinking that when you the surface might change when you have water molecules on the surface forming hydroxyl? That is very interesting because when we do electrochemistry, for example, water oxidation, some of us, well, in our community, we have seen some papers or some theory that during the electrochemical water oxidation process, the surface might have to go amorphous.
Mm-hmm. Yes.
And then to generate oxygen. So that is not difficult to understand because you always have this energy input to change the surface. But in your second part, you have shown a very nice cartoon animation that the surface just simply put water on the surface and then the surface structure completely changes. Am I right in thinking? So my question is, what is the driving force? What is the thermodynamic driving force to make that change? And in theory, is that calculatable?
Yes.
Thank you. Okay.
Yeah, so I mean, the reason why it reconstructs in the first place, right, is that some neighbors are missing. That's where surfaces reconstruct, right? You cut them, you make them in vacuum, you cut some bonds, the surface reorganizes to counteract that. You put water back, and then you alleviate that to some extent. So that's understandable. How, but it could also be that we know from other things, right, that it's not often that it's not always that it goes back to just what we call bulk terminated. You just cut it through. We know that depending on gas atmosphere and temperature and chemical potential, it can go to different structures. What these structures are, I think that's not so easy to predict. So it's been done in this particular case, and what we see is that our experiments seem to confirm these theoretical predictions. But I think you really have to go, to each case separately. So I think when you have something that's very stable, very low energy surface, and it's very simple, then there's a good chance it survives in bulk terminated conditions. When it's unstable, then things will certainly change. I mean, I once tried to write a proposal for this electrochemistry, and I was reading all this literature about people thinking that becomes amorphous and that this, really it's mass van Crevelen type mechanisms that you really, for this OER, for example, right, you really take in oxygen from the surface that then goes off. People can do that with isotopic labeling. They can see where the oxygen comes from this OER, right? And then I was really frustrated. I mean, I thought, okay, if things become amorphous, then with our methods, we cannot really see anything. So I stopped thinking along these lines. But, that's what people assume, right? That's my philosophical caveat. People assume this, right? Bulk terminated. This is what you get, right? You just get, these different intermediates. Very simple. It might not be correct at all.
I think it's widely applicable in electrochemistry, electrochemical water station. And for photo, for example, hematite, and we have fairly solid evidence showing that it doesn't oxidize the surface oxygen. Hematite only oxidizes the surface water. So the oxygen doesn't come from the surface structure. It comes entirely from the water molecule outside.
Because why you have this? Because of isotopic labeling or what?
DFT calculation and kinetic analysis.
Okay, I see. Because we have looked at hematite.
Yeah.
Recently, like last year, published a paper where we saw that there's massive scrambling, even at low temperature, between oxygen from the water, even in gas phase water, and the surface. I mean, it's immediate. It's really, we do this isotopic labeling water, and we can see the oxygen really goes in and out dramatically. Yeah.
Okay. Thank you very much.
Thank you.
Thank you for your answer. Wonderful.
Thank you, man. Let me see. So we have, maybe I can ask one more question related to amorphous states. Ulrike, have you ever tried to do STM of amorphous surfaces? Is there something that we can learn from this microscopy approach? Because indeed, the amorphization is very, very common whenever we drive the surface out of equilibrium too far.
Yeah, I mean, there's no, okay, so with this scanning probe microscopy, there's no limit to have something ordered, right, rather than amorphous. In principle, one can, provided it's flat. So for this scanning probe microscopy, you need a very flat surface. So if you have anything that's very flat, yet disordered, in principle, you can do imaging. But not much things have been done because it's difficult to get both things at the same time. Very often amorphous also means rough. And then you're lost because this, once you have that, you have the very sharp tip, and it's not only the last atom that interacts, but other atoms at the tip. But in principle, yes, in principle, you can certainly look at amorphous structures. Have we done it? No. Other people have. For example, this nice work from Freund on amorphous silicate overlayers, where they have really seen how these glass structures form.
And when you say flat for STM, you mean
flat,
like
flat.
Atomically flat over hundreds of nanometers?
Yeah.
Or, okay.
Yeah, ideally.
Hence.
The flatter, the easier.
Okay.
Yeah.
Yeah. Arti, go ahead.
Thank you so much. Thanks for a very interesting talk, Professor. My question is related to the second half of your talk, where you were mentioning about changing the pH by dosing water along with CO2. So, how did you calculate the pH? Was it calculated or was it measured?
No, just calculated. It just, you can easily go to Wikipedia. The student did these calculations, but actually you can easily go to Wikipedia and just look at the equilibrium between partial pressure of CO and what you would expect. Now, we have not measured it. We've thought about ways to really measure it in our acidic drop, but we haven't done it. So these are just expected pH values.
Okay, right. Yeah, because I was wondering, like, how would you be able to measure for just one drop having the probe inside? It seems difficult experimentally. That's why I asked.
Yes.
Thank you.
Sure. Thank you.
All right, maybe I will have a few more questions and we will wrap it up for today. One thing that I think is very important for whenever we work with surfaces is to, especially for oxides, is to know that they can be quite polar.
Mm-hmm.
So maybe you can also comment on that, like how we can study this polarity effect on the adsorption,
Mm-hmm.
and if we should be really that careful about it, maybe not, because it can lead to not only restructuring, right? It can lead to loss of, say, oxygen or reconstruction in electronic properties.
Yeah, so the surface polarity is, of course, a running theme in oxide surface science ever since the field was born, which was like in the 90s. I can tell you that these electronic reconstructions are not lower surface energies, not as much as real massive chemical reconstructions. So normally, if you have a polar surface and you give it just a little bit of thermal energy to go towards equilibrium, what will happen is that that the surface will massively restructure. It will not just be like in DFT calculation, you put up a polar slab, one is positively charged, one is negatively charged, the electrons will go to one side and will make a two-dimensional electron gas. I don't think that happens in real life. In real life, what will happen is that, you know, surface, actually in this paper, we've looked at potassium tantalate, which is an intrinsically polar surface. And we looked in, when you cleave it, you know, how is polarity alleviated? And first it is electronic. Then if you I go up in the temperature just a little bit, things start to move. You'll form vacancies, oxygen vacancies, by just lateral motion. At some point, there will be a restructuring of the whole surface to alleviate the surface polarity. And if you put a little bit of water, then the whole surface will change again. So in the end, whenever you have a polar surface, I think it will have, the first thing the surface will do is automatically lower its surface energy by doing some sort of restructuring. That's my experience in this.
Mm. But you mentioned DFT, so does it mean that such surfaces are a tricky thing to calculate with DFTs?
Yes, so in this case, you know, it's polar, but we took, this is a polar surface actually, depending, it's a perovskite surface, but because it's potassium tantalate, it's intrinsically polar, so you have charge, positive and negative charges. What happens is that the surface that's half covered with one and the other one not, that will be non-polar right away, so there will be some local rearrangement to do that. In this particular case, you can set up your slabs so that it, you know, it goes up and down, so it's like symmetric slabs, and then it's easier to do in DFT calculations. So you don't build up this field, right? That really
yes. That was my point. Mm-hmm.
Yeah. So you just make symmetric slabs so that it goes up and down and up and down and up and down.
Okay. Okay, I have one more question from the from our audience. So please go ahead and ask, and then we will finish it.
Yeah, I have a question on the pKa. You at the end of your talk you mentioned. So if we take the oxide surfaces, we have different absorption sites, right? Which behaves differently, and those different absorption sites could have like different pKa values. Yes. So how do we determine the pKa of the system as a total?
Yeah, I mean the pKa. Yeah, that, you know, I'm not a chemist. You ask me much. You know, people determine the point of zero charge, right? So that you can determine experimentally by just changing the pH and see at which point the surface is no longer charged. I guess there's ways to look at the overall behavior, the macroscopic one, but people are interested in finding out the microscopic one, right? Because if you can change that, maybe you can change the pKa value. Overall, you can determine it, but for chemistry, the local thing matters, right? If the local pKa is different, then it will behave differently.
Mm-hmm.
I think overall, you can do that, right? You can just look at this, when does your charge, this type of things. But locally, it's difficult.
Mm-hmm. Mm-hmm. Yeah, from your slide 10, there are different absorption sites for titanium dioxide. So that could lead to different pKa values from DSP calculation.
Right, in this paper, for example, they calculated a different pKa value for this site, dramatically different than this one. And then if you average both out, is that what people get macroscopically? Yes.
Okay, thank you so much.
Sure.
Thank you, Ulrike. Maybe you can give us your final opinion about the future of this field. So where things are going and where you think it will be still feasible to do experiments, to what extent then this breach between the liquid or electrochemical experiments and the UHV experiments, to which limit those bridges can be built?
Yeah, there's a lot of effort to do that, right? And I think it's really important to do that. There's lots of interesting things going on right now. For example, doing things with methods that can be applied also in liquids. I mean, one strength of surface science has always been to develop new methods. And now there's a big push towards developing methods that also work in electrolyte under these conditions. We have acquired this atomic scale understanding, and often people try to do that and lose it along the way. I think that's the real tricky part. My feeling is maybe sometimes it's going a little bit too fast. That people just take a single crystal and think, okay, that's not atomically controlled. To really do it atomically controlled, I think it's not so easy, and you have to go to great lengths. And I can see that people really try to do that in a good way. It has, see, if you look back actually historically, the very first surface science experiments were actually done because of electrochemistry. And then these two fields kind of deviated. And now I can see them coming back together. And I can see that things that, people do with surface X-ray diffraction or doing with, this very sensitive non-contact AFMs, I think can really help to understand things better. So I think actually merging these two things together with theory, I can see, I think it's a bright future. Okay.
Thank you. So thank you so much for your excellent talk. And of course, especially for staying for so long and answering all the questions. So we answered a lot more questions than normally. Thank you so much. It was
Thank
great
you.
talk.
Thanks for asking questions and thanks for hanging around.
Thank you. Have a nice day.